Hi, in this module I will discuss thin pressure vessels. The systems that store fluid under pressure are called pressure vessels. Pressure vessels are thin if the ratio of inner radius to the wall thickness T is greater than 10. That is, if radius R to thickness T is greater than 10, we say that pressure vessel is a thin pressure vessel. Thin pressure vessels may be cylindrical or spherical in shape. First, I will discuss thin cylindrical pressure vessel. Consider this thin cylindrical pressure vessel which is subjected to pressure P from inside. Due to this pressure vessel P, the material will move in the radial direction because this pressure is acting along the radial direction. This is thickness T of the cylinder before deformation, and this is the radius Ri. This is radius R0. We can say R0 is equal to Ri plus T. But since this thickness is very small for thin pressure vessels as compared to the radius, therefore we can neglect thickness and we can directly write R0 as approximately equal to Ri. So when this pressure vessel is subjected to pressure P, then it will move in radial direction. Consider the cross section of this thin cylindrical pressure vessel. When pressure P is applied, then the cross section will move in the radial direction like this. So if we compare this deformed cross section with the original cross section shown by this dotted line, we see that all the points on the cross section have moved by some radial displacement. The outer surface has also displaced by some radial displacement. Also, if we see that at any radius r inside the material of the cylinder, then this cross section at any distance r has also displaced by distance ur. So this cross section at any distance r has moved again by this distance. We call the displacement at any r is equal to r as ur. So this displacement at any r is equal to r is ur. So this displacement is ur. This displacement is also ur. That is radial displacement at any location r. So if we see this on this diagram, the initial cross section was having radius Ri and outer radius as R0. Therefore, this is the thickness of the cylinder initially. After the application of pressure, this cross section will move in the radial direction. So, if we consider any element which is at a distance r, that is the element shown by this red dotted line, then after the application of pressure like this inside surface, this red dotted element will also displace by some radial displacement. Let the radial displacement at r is equal to small r be ur, where ur denotes the radial displacement at r is equal to r. Now, in the analysis of thin cylindrical pressure vessel or thin spherical pressure vessel, we will assume that there is no change in the thickness of the cylinder even after the application of pressure. That is, if the original thickness was T, this was the original thickness. If this original thickness was T, then after application of pressure, the thickness still remains T. That is, there is no change in the thickness of this cylinder, though the cylinder material has displaced in the radial direction, but still its displacement is such that the thickness T remains same. For thickness T to remain same, the displacement of point A to point B must be same as the displacement of point C to point D. Therefore, we can say that the radial displacement at point A, that is UA, and the radial displacement of point C, that is U at C, must be same, because if the inner point and outer point are displacing by unequal amounts, then the thickness T will change. But since we are assuming that thickness T is not changing, therefore we will assume that the radial displacement at all points along the radius is same. Now, if we want to find radial strain, that is strain of the cylindrical element in radial direction, then we choose any differential length at r is equal to r. Let this differential length be dr. After the application of pressure, point E, that is this point, and point F, that is this point, will move in radial direction. So the point E will now move to some E dash from E, and point F will move to F dash from point F. We have seen that initially EF was of length dr, and now this E dash F dash can be found by knowing that this displacement is UE and this displacement is the radial displacement of point F, that is UF. We have already learned that UE will be equal to UF because all the points along the radius will displace equally in radial direction. Therefore, point E will also displace by U and point F will also displace by U. Since both the points E and F have moved by same distance in the radial direction, therefore there is no relative motion between point E and point F. So we can say that the length EF, that is dr, has not changed. Therefore, the change in length of a differential element EF along the radial direction is 0. Therefore, we can say that the radial strain in this case is 0. That is, radial strain epsilon r is equal to del u by del r is 0, because all the points will move equally in the radial direction. That is, there will be no radial relative displacement, that is del ur will be 0. So the radial displacement in case of thin cylindrical or thin spherical pressure vessels will be 0. So thickness will remain same even after application of pressure. But due to the radial displacement, there is change in the circumference. For example, consider this element at any distance r as shown by this red dotted line. The circumference before the application of pressure is 2 pi r. But after the application of pressure, this red dotted line has moved by radial displacement ur to new cross section shown by this solid red line. So the circumference has changed from 2 pi r to 2 pi r plus ur. So we can say that due to the application of pressure, there is radial movement, and because of radial movement, that is radial displacement, there is change in circumference, but there is no change in the thickness. So radial strain will be 0 because there is no change in thickness along the radial direction. However, since circumference is changing, so we can say there will be strain along the circumferential direction, because this circumference, which was initially 2 pi r, has now changed to this circumference. which is 2 pi r plus ur. So there is a strain in the circumferential direction. Now we can find circumferential strain. Circumferential strain, denoted by epsilon theta, can be written as change in circumference divided by original circumference. Now the change in circumference is the final circumference, which is 2 pi r plus ur at any distance r inside the thickness of the cylinder, minus initial circumference at r is equal to r, which is 2 pi r, divided by the original circumference, which is 2 pi r. So we can write epsilon theta as just 2 pi will cancel out, and r will cancel out, so we will get ur by r. So there is circumferential strain because of radial displacement ur. Now we know that r lies between ri to r0, because this is the cylinder, the inside radius is ri, the outside radius is r0, and this is some r. So r will be lying from ri to r0. But since ri is almost same as r0, that is, there is not much difference between ri and r0, because thickness t of the cylinder is very small. Therefore we can say that ri is equal to r0 is approximately equal to r, because r lies between ri and r0. Therefore we can replace this small r by some r mean, where r mean is equal to ri plus r0 by 2. However, if in the thin cylindrical pressure vessel ri and r0 both are not given and only ri is given, you can replace r mean by ri, because ri is almost same as r0 and it will be same as r mean. So we can say that circumferential strain E theta is equal to ur by r mean. Now since ur is constant, because this ur is not a function of r, since all the points are displacing by same amount in the radial direction. So ur is constant and this is some mean radius which is a constant. Therefore circumferential strain in case of thin spherical or thin cylindrical pressure vessel will always be constant. So now let us find the stresses that are induced in the thin cylindrical pressure vessel due to the application of pressure P from inside. When a pressure vessel is subjected to internal pressure, three mutually perpendicular stresses will be set up in the vessel, namely the longitudinal stress, the circumferential stress or the hoop stress, and the radial stress. For a thin pressure vessel, it is reasonable to assume that radial stress setup is small in comparison to longitudinal and hoop stress. So for analyzing thin pressure vessels, we will be assuming that the radial stress is negligibly small. We have already seen that the radial strain epsilon r is 0 because there is no change in the thickness of the cylinder along radial direction. So we will also assume that radial stress is 0 as compared to longitudinal stress and the hoop stress. Later on, I will also justify that assuming radial stress to be negligible will not induce much error. So first, let us find the longitudinal stress. Consider this thin cylindrical pressure vessel which is subjected to pressure P. Because of this pressure P, longitudinal stresses will be developed in the pressure vessel. To find these longitudinal stresses, make a cut in the pressure vessel like this that divides the thin pressure vessel into two parts. So these are the longitudinal stresses acting on this part. Now consider this part. Since the entire cylinder was in equilibrium, therefore this part of the cylinder must also be in equilibrium. For this to remain in equilibrium, the force exerted by the pressure must be same as the force resisted by the stresses. So we can say that for equilibrium, pressure force must be equal to the resisting force. The force of the pressure is given by pressure into the area on which pressure is acting. So pressure is acting on this entire area. This is radius Ri. So we can say pi r square. Ri and r naught are almost same because it is a thin pressure vessel. And the resisting force is given by stress sigma L into area on which the longitudinal stress is acting. Longitudinal stress is acting on this blue shaded area, and this area can be written as 2 pi Ri into T. Ri and R naught can almost be taken as same. This is thickness T. So from here we get longitudinal stress as P R by 2T. Now circumferential stress or hoop stress. This is the stress which is set up to resist the bursting effect of the applied pressure. Consider this cylinder which is subjected to pressure P. This pressure P is a load acting on the cylinder which is trying to burst the cylinder into two parts like this. So this pressure and this pressure, they are trying to separate the cylinder in two parts, one this and one this. This is called as bursting of cylinder. But this bursting is resisted by the internal forces which are acting on the material of the thickness of cylinder. So if we draw this diagram, we can see that there will be stresses acting here which will be trying to resist this pressure P. These stresses are called as circumferential stresses sigma theta because they are acting along the circumference. So if this is the cross section, stresses are acting along the circumference. So these are circumferential stresses. So if we see this on this diagram, these all are the circumferential stresses sigma theta. So along the thickness T, circumferential stresses are acting to resist the applied pressure P. So the resisting force can be written as sigma theta, that is stress, into area on which this resisting stress is acting. The area on which it is acting is this length L into thickness T. So it is T into L. This is on this side and similar will be acting on this side. So we can write it as twice. So resisting force is 2 sigma theta TL. Now the bursting force. The bursting force is given by pressure. So pressure will be acting on every cross section like this. On this cross section, pressure is acting at all the points. So it will be acting along the entire length of the cylinder. Here, here, here. On every cross section, pressure force will be acting and trying to burst the cylinder into two parts. So if we consider any section, pressure distribution will be like this. So if we see pressure distribution, we can see that it is symmetric about this line. Now this pressure P will have two components, one horizontal and one vertical. This pressure will also have two components, one horizontal and one vertical. So horizontal component of this will be acting in this manner and horizontal component of this will be acting along this direction. So these two horizontal components will cancel out, but the vertical component of this pressure P and the vertical component of this pressure P will add on. So the net effect of this pressure on this section is exert a vertical force, and similarly on this cross section a net vertical force will be acting, similarly on this cross section, similarly on this cross section. So on every cross section a net vertical force will be acting due to pressure P. This net vertical force due to pressure can be found by simply finding the vertical component of this force. The vertical component of this force exerted by the pressure is pressure P into the projected area. So if we project this area, that is if we project this curved surface area, then it will be, if this is diameter D, then it will be diameter D, and along the entire length L, if we project, we will see that it will be L into D. So on one cross section, if we consider this section, on one cross section we are getting D, and if we project for every cross section, for this, for this, for this, for this, so we have to project along the length L. So the complete area of projection that we are going to get will be L into D. So the force due to pressure will be pressure into area, which is pressure P into L into D. So this is the bursting force. Now for this hemi-cylinder to remain in equilibrium, the bursting force given by pressure must be equal to the resisting force given by the sigma theta. We have already found the resisting force as 2 sigma theta TL. So for equilibrium we equate them. Resisting force is equal to bursting force. Therefore we can write 2 sigma theta T into L is equal to P into L into D. Therefore we get sigma theta is equal to PD by 2T. So this we get as PR by T. So this circumferential stress is also called as Hooke's stress. Now that we have found stresses on the thin pressure vessel, we can find strains in the thin pressure vessel. To find these strains, we can use Hooke's law, assuming the material to be linearly elastic and isotropic. The Hooke's law says that the strain epsilon xs is given by 1 upon E into sigma xx minus mu sigma yy plus sigma zz. So x is perpendicular to y is perpendicular to z. We have seen that the longitudinal stress sigma L is perpendicular to the Hooke stress sigma theta, because sigma L is acting along the length and theta is acting along the circumference. So they both are perpendicular to each other, because if we see the cylindrical section, we can see that the sigma theta will be acting like this and sigma L will be acting like this. So this is sigma theta and sigma L. So they both are perpendicular to each other. So we replace epsilon xx by epsilon theta. So we have to write here sigma theta minus mu and sigma y, which is perpendicular to x, by sigma L. Sigma z can be the radial stress sigma r, but we are assuming that radial stress is negligible. Therefore we can write 0 in place of radial stress for thin pressure vessels. Therefore we get Hooke strain or circumferential strain as sigma theta minus mu sigma L. But we have already found that sigma theta was PD by 2T and sigma L was PD by 4T. So we can write epsilon theta as equal to 1 upon E. PD by 4T can be taken common. So we get this as 2 minus mu. So this is the Hooke strain in the thin cylindrical pressure vessel. So this is for thin cylindrical pressure vessel. Now similarly we can find the longitudinal strain epsilon L. Epsilon L will be given by 1 upon E into sigma L minus mu times sigma theta, because theta is perpendicular to L. So putting the values, we can get longitudinal stress we found as PD by 4T and Hooke stress sigma theta as PD by 2T. Therefore we get longitudinal strain as 1 upon E. Again PD by 4T can be taken out. Therefore we will get this as 1 minus 2 mu. So this is the longitudinal strain. And the radial strain epsilon r was del u by del r, which was assumed to be 0. Remember that the circumferential strain E theta was also found as UR by R, but we have also find epsilon theta as equal to 2 minus mu by E into PD by 4T. Now we can also find what is the change in the volume of the cylinder due to internal pressure. That is, we want to find the volumetric strain epsilon V. The volumetric strain is given as change in volume divided by original volume. The volume of cylinder is given as pi r square into L. Therefore, the differential change in volume can be written as pi into r square dl plus L into 2r dr. Therefore, we can write volumetric strain as pi r square dl plus 2rl dr whole divided by the original volume, which is pi r square L. Cancelling this, we can write epsilon V as dl by L, because r square and r square will cancel out, plus 2 times dr by R. So this is the volumetric strain for thin cylindrical pressure vessels. Now we can write this dl by L as change in length upon original length, which will be the longitudinal strain, plus 2 times. Now this dr by r is change in radius by original radius. So if we multiply the above term by 2 pi, then we get 2 pi r, and below also if we write 2 pi, we get 2 pi r. So this is change in circumference divided by original circumference. So we can write this as epsilon theta, that is change in circumference upon original circumference is circumferential strain epsilon theta. But we have already find epsilon L as 1 minus 2 mu by E into PD by 4T, and epsilon theta as 2 minus mu by E into PD by 4T. Therefore, we get volumetric strain as 5 minus 4 mu by E into PD by 4T. So this is the formula for calculating volumetric strain of thin cylindrical pressure vessel when it is subjected to pressure P. Now, why we have neglected radial stresses in the analysis of thin pressure vessels? We can see that when this cylindrical pressure vessel is subjected to inside pressure P, consider this point. A differential element is shown by this red shaded area. On this differential element, a pressure P is acting from inside. So if we want to write the radial stress at R equal to Ri, that is in the inside radius, then it will be minus P, because it is compressive in nature. And if we consider this small element on the outer surface of this thin cylindrical pressure vessel, we can see that this outer surface is subjected to atmospheric pressure from outside. Now if we are taking this pressure Pi as gauge pressure, that is pressure with respect to atmosphere, then the pressure acting here will be 0. Because if we are taking gauge pressure here, here also we have to take gauge pressure. Then since the pressure acting here is atmospheric, therefore here gauge pressure is 0. So we can say the radial stress at R equal to R naught, that is the outer radius, is 0. So radial stress is varying from minus P to 0. So the maximum value of radial stress is P. But we have already found that hoop stress is given by PD by 2T. So hoop stress is equal to pressure into D by T. For thin pressure vessels, we have seen that D by T is large because the thickness of thin pressure vessel is small. So hoop stress is pressure into D by T, which is a large term. So pressure into some large term will make hoop stress as very large compared to this pressure. Now, since the maximum magnitude of radial stress is P, therefore we can say that sigma r is negligible in comparison to sigma theta, because sigma theta is already P and we are multiplying d by t, which is a large term. So we can neglect radial stresses in the analysis of thin pressure vessels. Now, thin spherical pressure vessels. As with the thin cylindrical pressure vessel, radial stress is assumed to be negligibly small in comparison to hoop stress and longitudinal stress. Because of the symmetry of sphere, the stresses set up due to internal pressure will be two mutually perpendicular hoop stresses or circumferential stresses of equal value, as can be understood from this diagram. So if we cut the spherical pressure vessel, then if we cut it along this direction, then this is a circumferential strain, and if we cut along this direction, then also it is a circumferential strain because it is acting along the circumference. So there are two hoop stresses or circumferential stresses along two perpendicular direction, one along this and one along this. Let us call this as sigma theta and this will be sigma phi, and theta and phi are perpendicular to each other. It is to be noted that because of the symmetry, sigma theta will be same as sigma phi. So let us find sigma theta. Now this resisting force will be given by the stress sigma theta into this resisting area. So the resisting force will be sigma theta into shaded area. If we consider this as the radius Ri, R0 are same because this pressure is thin pressure vessel. So 2 pi Ri into T. And we want to find now bursting force. The bursting force will be given by the pressure which will be acting all along the surface area of this hemisphere. So the vertical component of this pressure will be given by pressure P into horizontal projected area. So if we are projecting this, we will get a circle with radius r. So the bursting force will be pressure into pi r square. Now for equilibrium, the resisting force given by sigma theta must be same as the bursting force of pressure. That is, the resisting force must be same as bursting force. So we can write resisting force as sigma theta into 2 pi r t and bursting force as pressure into pi r square. Therefore we get hoop stress as sigma theta equal to p r by 2t, which can also be written as p d by 4t, and this will be same as sigma phi because of symmetry. Now strains in thin pressure vessel. We have seen that theta and phi are perpendicular to each other. Therefore we can write epsilon theta as equal to 1 upon E into sigma theta minus mu times sigma phi, neglecting the radial stress sigma r. So we can get this as sigma theta and sigma phi are common, so we can take them out, 1 minus mu. So epsilon theta will be 1 minus mu by E into PD by 4t, because sigma theta is PD by 4t. Now change in volume of spherical pressure vessel due to internal pressure. We have learned that the volumetric strain is given by change in volume upon original volume. The volume of a sphere is given as 4 by 3 into pi r cube. Therefore the differential change in volume will be 4 by 3 pi into 3 r square dr, which will be 4 pi r square dr. So therefore we can write this as 4 pi r square dr divided by 4 by 3 pi r cube, which is the original volume. So we get this as 3 times pi cancel out, 4 cancel out, so we get this as 3 dr by r. Now this dr by r can be written as 3 times d 2 pi r divided by 2 pi r. So this is change in circumference by original circumference. So we get this as circumferential strain epsilon theta. Therefore, we can write volumetric strain epsilon B as 3 times sigma epsilon theta, and epsilon theta was 1 minus mu by E into PD by 4T. So we have found the volumetric strain in spherical pressure vessel due to internal pressure P. This ends this module. Thank you.